is that there's just a lot of practicality to this when it comes to getting this reaction to occur the way you want it to occur, which is via electrons. I'll try to do it from right to left, but it depends on what is in solution, which is what we're covering today. So I just pointed out that the reality is you need electrons to go from one way to the other, and you need to not short circuit it. And so the way to do that is to basically put a large amount of distance between, these are the electrodes. You need to put a large amount of distance between them so the electrons just don't go through the salty liquid. So why do you even have a salty liquid? Because one of the coolest things about batteries is that your current, which is the most important thing, because current is power, not voltage. 10,000 volts is nothing if there's no current. There's nothing even happening without current. That's actually limited by the transfer of ions. So if electrons are going from here to here, you have to just, I don't want to mess up the drawing, sorry. But if electrons are coming from here to here, this is getting negative and that's getting positive. And that's going to stop the battery really, really quickly, like in a second. That's a dead battery. So what you have to have, if you have to have negative ions, not electrons, ions, move over here, and cations vice versa, to basically negate that. So, and I talked a little bit about salt bridges, but whatever. Anyway, it's just so ions move left and right, and that really is the challenge in battery design. It isn't so much getting the electrons to flow, it's getting the ions to flow so that the electrons can flow. They're actually the hard part, and that's actually the biggest challenge with lithium batteries is getting the lithium. See, you notice that lithium, you know, what's the big deal about lithium? Oh, I don't know, that's just how they make them. Lithium is a tiny ion, right? It's easy to move. Why's the focus on lithium, you know, so important? That's the ion that moves inside the battery, and it's easy to move because it's a tiny little sucker, right? So some of the bigger advancements people are trying to make, the advancements they hope to make are actually to get something like sodium, because chemically it's a lot easier than lithium, and to get ions that have more than one charge, because then it's 2 for 1. If you get a dication to move from one side to the other, it brought 2 electrons with it as opposed to 1. So what you will not see, this seems like a true and false question, you will not see gigantic heavy metals for multiple reasons with low charge inside of a battery, not just because of toxicity, yeah, that's bad, but because they wouldn't move quickly, and that means you wouldn't have current. So anyway, that is an engineering problem. I just think it is kind of neat, and being college educated, I would want you to know things about batteries, and there you go. Now, this is as far as I got last time, talking about how, at first I just mentioned if this was zinc and this was copper, the way you know what's being oxidized and reduced, we went over those words I don't really care too much about, is that copper is being plated, so you see the copper, it would help if I drew it right. You will see the copper electrode grow and the zinc dissolves, and that's why you know what's doing what, so that's just a practical issue. And so that allows you to write out the full reaction. I'm going to go into great more detail about how this works. The way that this is written out, so it's my oxide red, so you write out what's being oxidized and then reduced. And the way you do that, in case you see this notation, say like on a GRE or an MCAT, I really don't know what's on the MCAT, I heard some changes, but this would be on a GRE, so I think it's important to cover. What you do is, so we're going to start with the oxidation, and zinc is being oxidized. Remember, that's a loss of electrons. Remember, gaining negativity reduces you. Gaining electrons is reductive. That's easy. Oxidation is a little harder because it has so many definitions. Anyway, zinc is being oxidized. It's losing electrons. So you begin with my oxidation. Then what you do is in the notation, you draw a vertical line to represent a phase transition. Of course, that is a salt. And sometimes I see this expressed just this way, but some people like to remind you that there's a counter, which kind of makes sense. SO4 is 2 minus, is that right? God, I forgot. Yeah. I hope so, because that's what I'm going to do. Okay, then a salt bridge. Now remember that when it comes to advanced batteries, any battery, you don't actually have salt bridges. You don't see a little tube sticking out of your battery. the way there is a component that represents a salt bridge. It just doesn't look like this simple Daniel cell. Anyway, you draw that with a little double line, and now we're going to do the reduction part. And these are just going to be mirror images with copper. So I'm going to have copper 2+. Of course, that will be a sulfate because sulfuric acid is commonly used in these. And sulfuric acid, I think the most commonly produced, the number one chemical produced in the world, if I'm not mistaken. And then you end up with the reduced monoxide, reduced electrode. Anyway, that's just the notation. I've never tested on this. I don't think it's that. This is an example of memorization, and I try my best not to do that. Okay, now, so definitions done. You know, I don't care too much about that, but you might see it on a standardized exam, so there it is. Now I want to cover stuff that's kind of a lot cooler, which is how you know this to begin with, other than you just set it up. Well, sorry, someone set it up a long time ago, so you don't need to. So what data did they give you? So let's forget about zinc and copper electrodes. I don't think I'll come back to that. I'll give much more interesting and relevant examples. Okay, this is a neat one. And again, this does represent what people are trying to do in more advanced design of not new materials, but new battery design, which is air batteries. Draw this right. And so to introduce the concept of an air battery, I'll do hydrogen going through a little tube. Okay, so those are hydrogen bubbles, by the way. This is a detail. The electrode will be platinum. That's not a big deal. Actually, I think this is done. Platinum is done for one so that it doesn't corrode. There's some other reasons, but it's not go nuts on it. Okay, my point being is that there are such things as gas batteries, which is really, I think it's kind of fascinating, just myself. And God, what else want to tell you about gas? So, and that's also what people want to design in the future for, like I mentioned to you, would you get on an airplane that was battery powered? I would hope not. That's pretty scary, right? Only some jackass in his backyard is building something like that. Don't get on it. All right, but people do think, I mean, we are going to run out of kerosene, we are going to run out of jet fuel, we're going to run out of gasoline, which is the old-timey airplanes with the rotary type of motors. We're going to run out of those too. So people think that a lithium air battery is the way to go because that can produce the kind of power of a gas, a regular like car engine. Jet engines are infinitely more powerful, but like my point is, we're not going to be flying jets much longer. Okay, so this is an example of a gas battery, and now this is something that I'm kind of fascinated with, but let me be more clear, this is how I'm adjusting. This is the kind of thing I will put on a test, right? I used to not say that. I used to say this is very interesting to me because I'm putting it on a test. Now you got it, okay? What's cool about this is that you can actually get multiple things happening. And I'm going to go over this in the next, in the extra hour because it'll be on the homework and as I am going to very clearly state, it will be on a test. There are two possibilities. That's the coolest thing about this stuff, is that a lot of the things you can put into these little buckets, and again, advanced batteries are the same, they're just in a more engineered form. But there's different things we can put in these buckets, but there's also, if I put some particular ion, it might be able to do one or more things. Let's focus on more. So what I have you do, and I'll show an example, is how do you decide? Basically, I'm going to fill this with X and Y. How does the battery work? And I'll give you, if I gave you like, here's a possibility for X and Y, and that's all you have to work with, well, there you go. You just work with that. But what I'm going to do is give you, in this case, two possibilities. And then I have only one will occur, and the other one, I won't screw you too bad. I'll just give you one thing to figure out. So that's how I test whether you actually know this stuff or not, all right? Okay, now why am I even bringing this up? Is let's put something different over here. Let's try, what am I going to do first? Let's try copper. Okay, so this is the hydrogen. It's called a standard hydrogen electrode on the right, and I put copper on the left. And what happens is, I have to read this, copper will plate out onto the electrode. So copper is, I must have Cu2 plus ions in solution, so I have a copper sulfate. You need that no matter what for the salt bridge. And what I find is that the copper electrode is growing, so therefore I know electrons are going from hydrogen, so I'm losing H2 gas. Now I could have told you that, but realistically that's hard to know, right, because it's just bubbling. So I'm consuming this and I'm creating copper metal, and that allows me to draw this out. Again, I don't see myself testing you on this. So what's being oxidized is the protons. You know, I don't think I'm supposed to do it this way, but I'm going to do it this one anyway. I want to make sure that the stoichiometry is right. Before I said this screwed up. Okay, and again, the copper must be reduced for it to plate out. Okay, that's what's happening. Now there's a voltmeter up there, and that voltmeter reads 0.34 volts. Okay, so there you go. All right, so what? Well, hold on a second. I want to go over a couple things, and then it's all going to make sense. All right, I took that out, took out the copper, and I added zinc. Now, zinc does the opposite. Zinc starts to dissolve. All right, so it's not hard to figure out, well, before this was happening, so that means that that's happening, and that's correct. So that means that zinc is being oxidized. Okay, salt bridge, and that means I've got hydrogen being reduced to hydrogen gas. Okay, I measure that voltage. It is minus 0.76 volts. There you go. All right, so what? What this does, this information has been tabulated. This is the information in the table in the back of the book for electrochem. These are your delta G's of formation for batteries, right? This information right here. That's why this, remember I said before, this is the scalar hydrogen electrode. I used to test on this, but I won't anymore because it's kind of factoids. The neat things are that the conditions have to be, you know, perfect just like they are for the table in the back of the book. You can imagine that the hydrogen gas pressure has to be a bar. It has to be measured at 298, yada, yada, yada. The solution, by the way, the acid solution, right, because we need that, is 1 molar. Not going to test you on that because whatever. Maybe it's on the standardized exam. Okay, back to task. You're given this information in a table. Actually, what you're given are standard reduction potentials. You're told the voltage of reducing something. What you're not told is the fact that it was measured against hydrogen. You either know it, or if you don't know it, it actually really doesn't matter. So what happens is, and again, if this is the numbers in the table in the back of the book, what you do is you can add these together. Now there's a slight problem here, and that is that voltages, if you recall, let me, where do I have that information? This is a bit of an aside. I'm going to keep working downward here. This is an aside. You might should write this down. Voltage, remember, which gets the letter E for some weird reason, is this guy. Again, the number in the table in the back of the book, which is now not the formation G, but the EMF, the electromotive force. Again, I don't care if you remember that, minus RT, again, number of electrons in the reaction, Faraday's constant, which again, you don't need to know. Okay, there's this, but I told you I'm just going to table this part because it just really doesn't matter. This again is the products over reactants. If it's air, hydrogen, if it's an air battery, then these are partial pressures of products over reactants. However, batteries are designed in such a way that this just doesn't really do that much. And batteries are designed, engineered so that Q doesn't change too much as the reaction occurs. You would do that by like having the consumed chemical be in the form of solid so that they can kind of keep delivering until they're finally just spent. A lot of clever things engineers have come up with, oddly enough. That's why they get paid a lot. But for the most part, I just want to ignore this. We're going to focus on this entirely. Okay, so now what I'm seeing here though is that, and this, remember, Ben Franklin, thank Ben Franklin for this. This is one of the harder parts. Positive voltages mean negative delta G's. Negative delta G's, remember, those are good. We don't think of negative as good, but that's wrong when it comes to energy. Negatives are good. Negatives mean it happened. Why am I building this battery if I don't want it to be a battery? Right, so what I'm seeing here is a bit of a problem in that zinc has a positive voltage. So what I think I want to do is I think I want to reverse that and create that the reaction on top. So what I'm going to do is, oh wait a minute. Yeah, it looks like I might have written something a little bit wrong here. I do, no, that's negative. That's definitely negative. Tell you what, yeah. Tell you what, I'm just going to actually, I'm not going to express it this way because after that I've just got a little bit confused. What I'm going to do is I'm going to rewrite the reactions as they occur on top, and I'm going to write out the EMS, and then I can convert them to delta G's. All right, so to do that, let me write what you find in the table in the back of the book, which are reduction potentials. Sorry for mine, got a little bit twisted there. Okay, again, this is the information you find in the back of the book. I may forget, it is actually terribly important that you write down what the phasors are. I may forget because they're either aqueous or solid. Again, there could be other examples. And then what I have is the EMF, which is in volts. Another little factoid, by the way, is that if I need to scale this reaction, remember, we are doing Hess's law, right? That sounds like a true and false question. We're doing Hess's law. This is actually a chemical potential because it's delta G divided by number of moles. So it's not going to scale. What will scale is delta G itself, which is actually, let's take the voltage and multiply it by the number of electrons, which now is extensive, which is basically delta G. Remember last time, again, I will not touch you on this, but Faraday's constant, you're never going to need to use it. We're just never going to need to use it. I'm just going to leave it at that. Okay. So there you go. I've got this. Now let me write down. Okay. Sorry. I'm getting an idiot. This would be. Yeah. Let me write this down. 1.52. Okay. This is 2 electrons. So I just take that, multiply by 2. Oh, right. Ben Franklin, thank you, minus sign. Okay. Now this is bad. This is bad. This is positive delta G. Divided by F, again, forget the F. This is positive. All right, so in terms of answering the question is, you got zinc, you got copper, tell me how the battery works. I'm starting with the first information, which was zinc, and I'm finding that the delta G is positive. Stop right there and write the reverse, because this is unfavorable. Right, in terms of figuring out how the battery works, considering a reaction that is thermodynamically uphill is inherently stupid. Do not do it this way. Immediately write down the reaction in reverse. Again, the goal is to figure out how the battery works. I told you that this is a zinc copper battery. I gave you the standard reduction potentials because that's what you find in the table in the back of the book. You found that this EMF is negative. If I reverse it, it's positive. And now the delta G is negative, which is good. These are in units of joules per coulomb, by the way. Again, factoid. Okay, great. Now I also gave you the reduction potential for copper. And again, I'm just writing down what I was given. Whether I can use it or not is another issue. I have to write it down first. Okay, so there's a reduction potential. The number I was given in the table in the back of the book or on your exam is this. And the delta G is 0.68, negative 0.68. Again, 2 electrons, don't forget the minus sign. Okay, now this is good. This is very good because now I can start making an evaluation. I got to figure out, the question again is I have zinc in one side, copper in the other. What happens? What happens is, what is thermodynamically downhill? I now see that this is thermodynamically downhill. This is going to happen on the zinc side. And so what about copper? Copper will conform. So this is the winner, and the winner makes the loser its, you know what. That's how that's how I want you to work these problems, all right? I'm going to be a lot more explicit about how to work problems from now on. Again, because this guy, it's like the big dog that grabbed the leash of the smaller dog. The smaller dog is going for a walk, whether it likes to or not. Maybe the dog will cooperate. This is the small dog cooperating, by the way. Or maybe it won't. I'll give an example of that. Now, why did I say that this is the small dog cooperating? It's because the electrons are on the right side. Right, you see Hess's law. I told you this is Hess's law. The electrons are on the right side, so now I can write out the net reaction. By the way, this is half the points on the test, is to get this part right. I'm going to give you two half cells, one of them which has two possibilities. I'll do an example problem in the next hour. And here, cancel the electrons. Okay, so now you got the reaction right. Okay, half credit, you know if this E is not good. Half credit. Now, the other part of the question is part A. Part B, what's part B? Part B is what's the voltage? The voltage, again, is calculated by Hess's law. I've got the delta G's, let's put them together. That's minus, and you better be getting a minus. 8, 0, 5, 2, 1.2, is that right? No, 2.1 plus 1, there we go. Okay, so that's joules per coulomb, it is not volts. The question in part B is what is the voltage? What is E? What that is minus the delta G, let me get this right. Here, let me write this out nicely. I'm about to kind of screw this up. Let me write it out nicely. So this is part A. Part B, you look at the equation in the back of the cheat sheet, that's the little problem that you had on the last test, and you see that the voltage is minus delta reaction G naught over F minus that number of electrons. Now again, do not try to memorize that. I'm going to give it to you, right? I just, why do I have minus? No, sorry, I'm being an idiot. Minus. I confused myself because the number is negative, that's what I did. Okay, so this is minus, now it has to be negative 2.2 joules per coulomb over F, which again doesn't matter, don't even write it down, and 2, which is 1.1 volts. Sorry, this does get a little bit twisted even in my own mind. That's why I had to work several examples, and on the test I'm going to have probably 2 questions like this, and you'll just, do it a couple of times until you just go on automatic. Again, the main thing is figure out, write out the equations if the delta G is negative, identify the winner, make the loser conform. Part A is getting the Hess's law high school level reaction correct. The next part is adding up the delta G's, just like Hess's law, minus divide by number of electrons. Why? Because that's the Nernst equation, and now you get the correct voltage. All right, now that demonstrates that you understand that batteries work via delta G. And that's what I want to see. That's all right. So, yeah, that's what I want you to see because that's how it works, right? Because there's 2 reactions that are set apart by the salt bridge. It's kind of funky how the winning reaction will force the loser to conform, and I'm going to do an example of that because it's probably not clear right now. And then, of course, the figure of merit on any battery. Sorry, I have to do it like this. If I well, watch the video. Yeah, I can't see that, but anyway. Oh God, what else do I want to say about that? Okay, yeah, so that's how I want to see you do this because that means you know how it works. But now let me give you the cheat sheet, like the Maxwell equation that gives you handy dandy answers and allows you to figure out whether you did it right. Now again, I want to emphasize, this is how it's done because this is how nature works. But there is a way to double check yourself that you can do instantly that tells you whether you're right or wrong. All right, so again, do this. I hate showing you this stuff, it drives me nuts. But I want you to get it right. Okay, so I'm going to show you the cheap way to do this, which is the way you probably learned it in analytical, which is to note that basically all you have to do is write the equation such that the voltages are positive, get the electrons to balance, and then just add them up. Add up the EMFs. So in that case, you notice that, here, I'm just going to pretend that this is all right here, 0.76 plus 0.34, look at that, it's 1.1. Right. So now my point being is that when I give you reductions, here's a battery, there's zinc on the left, there's copper on the right, that's the question. You're given that information on top, the reduction potentials. What you do is you make them both positive, figure out the winner, make the other one conform, and straight up add the voltages. Don't scale anything, don't scale the voltages. Remember, those are chemical potentials. They are intensive, they should not be scaled. Just add them together. Now let's say that the second one, the copper, the loser, had to be flipped because of its electrons, then this would be negative and you would just subtract the two. Right, that's again the cheating way to do this. Whatever, I look at this, I recognize that zinc is the winner if I flip it. I recognize that copper stays the same. They're both positive, I add them, I get 1.1. I do that, I write that off to the side, and then on the test I've asked you to do this, you do it and you get 1.1, move on, right? Go to the derivation question, right? Because you've done it right, so that's how you're gonna do it. Let me do one more example, and 2 or 3 more examples, and then we're actually gonna switch subjects here. Let me do I got 2 examples of harder ones that should hopefully cement the algorithm and understanding, but again, I'm going to try to focus a little bit more on algorithms for solving problems, more than I had been. That's how I'm going to bend. All right. Okay, so that was problem 1. Problem 2 is this problem. Let's do problem 2. You have a battery. Here's what's on the left, here's what's on the right. A, give me the reaction. B, tell me the voltage. Here's what you were given. You were given cerium, 4 plus, I don't know if you'd ever actually make a battery out of cerium. It sounds kind of dangerous, but actually I don't think it is. And again, this is the standard reduction potential. The number of the table in the back of the book. Notice that what I've done here, I've made the stoichiometry, I've got the stoichiometry screwed up. So now I'm playing games with stoichiometry. So now you're going to see how that part works. Let's look at the EMF, which is of course in volts. Again, this has to be given to you. Okay, they're both positive. That's good. Remember, positive voltages are good. Now let's get delta G. Remember, that's just minus the stoichiometry times the voltage given. Why would I not do that? Hold on 1 second.
It should be 2E, 2 electrons.
Not if I wrote it out correctly. Sorry. Thank you. You're right about that. My bad. I don't know why I did that. It's right in front of me. Okay. Now I've given you this. You write this down. Remember that this is delta G. The thing that matters is delta G. Forget the F again. Okay, minus 1.61, minus 0.68. Okay, now you tell me the winner. It's clearly this one. Now here's an example of the big dog dragging the little dog around by the leash. You see, this one is going to happen, and it is going to force this one to conform. But the electrons are on the wrong side now. All right, so I'm going to have to reverse this. Because what's going to happen is that this thing is basically sucking electrons out of, this is the one on the left. Sorry, I erased the battery. This is drawing electrons out of the other cell because it can't, essentially. This thing has no choice but to basically deliver them, right? It can't, this is consuming them, but this thing wants it so much more that it's just sucking the electrons out of copper. So what I have to do is I have to reverse this one. Okay, so let's just draw a line to that so we don't consider it anymore. Having established which is the winner. This is again the principle of the loser conforming. Okay, and now this is minus 0.34. Doesn't matter whether it's positive or negative. And, I think I actually have another problem. Yeah, I've got another problem. See, this is why I like this problem. I picked this one to actually run into two issues. One is getting the loser to conform, but now my electrons count don't work anymore, right? Now, the solution would have been to say have this one, but I'm going to actually do something a little bit more complicated. On your homework, you're going to see whichever approach I pick doesn't matter. What I'm going to do is a little bit more complicated. I'm going to take the winner and I'm going to double it. It does not matter which one you choose, by the way. You will always get the right answer. Okay, now what do I put here for EMF? What? I'm so screwed, people.
3 points.
No, it's intensive. Remember I told you voltage? All right, okay, all right, now on the test I just asked you this question, why didn't it change? I built you this table, I said I doubled this, why didn't the voltage change? How do you think of that answer? How do you get it right without trying to memorize it? Because that's the losing strategy. If I have a 9-volt battery and I make it the size of the planet Earth, what's the voltage? It's still 9 volts. There you go. Now you know. You'll get it right if I ask it on the test. All right, this is an intensive property. You can tell because it's joules per coulomb. Both are extensive. Extensive divided by extensive is intensive. Right, perfect. Okay, so this does not change, but this one does. All right, so this guy, let's see, this is plus 0.68 because it was 2 electrons, and then this is minus 3.22. Minus 3.22. Now the delta G, part A is get the reaction correct. Again, the electrons cancel. Another way to know this, did the electrons cancel? If not, you have done it wrong. Okay, so 2C4 plus copper goes to 2Ce3 plus copper 2 plus. Okay, part A is done. I'll label it that way. Part B is added up. Again, these are energy, so you just add them. Minus 2.54. That's in joules per coulomb. It is not. No, that's not in joules per coulomb. Is that not in joules per coulomb? No, that's in joules. Yeah, I kind of screwed up there. I think I said before that was in joules per coulomb. That's actually joules. Anyway, looks like I got a little bit off, so let me just say that the voltage, therefore the voltage, unfortunately the letter E, which is minus delta G over F over the number of electrons is minus 3.22. No, 2. What am I saying? 2.54. Looking at that, 2.54 over 2, 1.27, and that's in volts. That's in joules per coulomb, right? Okay, so there you go. This is another example. And now, hold on a second. Let's do the cheating way, right? Let's do the cheating way. Okay, the cheating way is to not do. Now I want to see everything I'm blocking off. Is what I want to see you do, but I don't need that to know whether, again, this is how I know if I did it right. I just need this information. Now the voltages are positive, and this again is the winner. Whichever one is the most positive, once you've done this analysis, getting the reactions the right way and scaling the number of electrons, once you've done that, it will always be true that the most positive will win. It doesn't matter how the electrons bounce around. You notice this, that I'm multiplying by electrons and then I'm dividing later? That's why it doesn't matter, right? It's a little complicated because there's a couple of steps, but again, the reason I can just look at the data given, make them positive, and pick the winner is because that all the scaling of electrons, while necessary to show me that you understand this, to get delta G's and add them correctly, ultimately you multiply by electrons and then divide them out later. So again, I'm given this information, they both have to be positive, I can pick the winner, the loser has to conform, so this is going to have to be flipped, which will make that negative, and then 1.61 minus 0.34 is 1.27. That's how I know I did it right. Okay. Tell you what, how about one more example? Let's definitely do one more example. And I've got two more for you. This one's horribly important. This is why we're all going to die. All right, so let me show you a redox reaction that's important for alternative energy. Because when I was your age, middle school and your age, I always wondered, why don't we just get solar cells? So this is an idea for turning solar energy into a fuel. You'll hear that energy solar fuels. The idea is that knowing that solar cells don't work at night, the idea is to use the sunlight during the day to create a fuel that you burn at night. Again, one of the solutions is to pressurize a cave. As nuts as that is, that's actually a really good idea. The other is to make fuels that you burn later. One of them is hydrogen. So my thought was, knowing that, again, nighttime is an issue, and that's when people use a lot of electricity, unfortunately, I always thought, why don't we just start sticking solar cells and just dunking them in water and generating hydrogen gas? Even if it's not efficient, let's just start doing it now and build up so much hydrogen gas that, in 40 years in Hubbard's Peak, we'll have tons of hydrogen gas. And at least it won't be so bad. Well, the answer is it doesn't work. Okay, so let me write down the reactions. Okay, and now here's a warning, and again, I'm going to do this in the next hour. Water and oxygen have multiple reactions, multiple redox reactions. So what I'm going to do, and I'm going to give you an example in the next hour, is what happens when I give you one side of the cell and there's two possibilities. I'm warning you, it's probably going to be water. Don't try to memorize that, just you're going to work with what I give you. But it's probably going to be water. Water can do multiple things, especially in the presence of oxygen. Okay. Now, the EMF, which is in units of volts, is 1.23. Now, again, a standard reduction potential is, I'm drawing hydrogen, obviously, H2. Wait a minute, what did I do here? My bad. Okay, sorry about that. I think I'm running my mouth like an idiot. Okay. All right, so again, water, oxygen. Oh man, there's like 4 or 5 of these that could happen. I'm just drawing one, so that's what we'll work with, which is the standard hydrogen electrode. Of course, that one would be 0 volts, because if you measure hydrogen in one side of the cell versus hydrogen on the left, nothing happens, right? Question?
Your hydrogen's not balanced on the top.
Sure they do. You notice that the oxygens didn't either? There you go. Yeah, thanks. All right. That is important because you got, well, if it wouldn't have been a disaster. It's a disaster if you don't get the electrons right. That you got to get right. Okay, so you're given this information. Now, I already know that this is the winner and the voltage is 1.23. But what do I want you to show me on the freaking test, which is the only thing that matters? I want to know that you turn this into delta G, and then you need to scale this. Let's see here. Okay, hold on. I've already established. Okay, this is the winner. This is the most negative. Look. See, this one's got to be reversed. This is the dog that's being dragged. Wait. I screwed up again. I gotta scale it. There, now my electrons, forget this for now, right? Now my electrons are being canceled. Okay, that's important. Here, let me just finish up part A. O2 plus plus H2 goes to 2H2O. Okay, right, so this is what do they call these? Fuel cells, right, on the space shuttle? That's how they made power. Okay, now this is actually still 0.0. This isn't the best example. Okay, so part A you got correct. The net result is minus, 4.92. And therefore, the voltage is minus 4.92 over the number of electrons, and that's 1.23 volts. Okay. Again, just another example, but the reason I want to bring this up is because it shows a lot about our energy problem and why that childish idea that I had of taking a solar cell and just dunking it in water and just generating hydrogen, even if it's inefficient. Does anyone know? All right, so solar cells, like the ones you played with as a kid that like spin around in the little glass vial, or the ones on older calculators, right, the solar cells on top. Does anyone know what the voltage is of those things? Off the top of your head? Now again, we tend to make these out of silicon, so it's a silicon substrate. And the voltage you get out of these, there's a little bit of variation, but anyone know? You don't know? It's 0.6 volts. 0.6 volts. Here's the problem. It needs to be at least 1.23. If it doesn't have that, it basically has no push to the reaction. And why is it a big deal? Because remember, the voltage isn't delta G. Delta G is right here, minus 4.92. That's gigantic. For some reason, our universe was made in a way that our most accessible fuel, which would be hydrogen, oxygen, and water, that's the greatest fuel we could ever consume. And God knows we consume a lot of energy. We have lots of water, so therefore we need to get energy from water and air. That would be the best thing we could do. But how many electrons? How many electrons? 4. Oh man, and that makes the delta G incredibly high. If it wasn't for 4 electrons, we would not have an energy crisis. We probably would still have too many people, but we would not have an energy crisis if this wasn't a 4-electron reaction, which, by the way, comes about because 2 waters make 1 O2. That's another fact. That's just how the electrons add up. It's because freaking water only has 1 oxygen, but O2 has 2. Means I've got a 4-electron reaction. Delta G scales with number of electrons, making this shockingly high. Regardless, that's the voltage, and when you compare that to our best solar cell, it's half as much as it needs to be. So you put a solar cell, dunk it in salt water, and what bubbles out? It begins with N and rhymes with a thing. Nothing. Nothing comes out of the solar cell. We've got no good way to make hydrogen from sunlight, and that's still where we're at. We've got no good way to do it.